We're given the quadratic polynomial f of x is equal to 2x squared minus 3, and we're asked to use differentiation from first principles to determine the value of f dash 2. That is the derivative when x is equal to 2. There's two ways you can do this. You can either use kind of the general formula for finding the derivative in terms of x, and then substitute in 2, or you can actually use 2 from the start. Now, I quite like to use the general formula. I think it's something, especially because it's something you can practice more often, and it's important to be able to do that anyway. So I'll show you how to do that, and then I'll show you how you could do it just by putting the 2 in. Now, the formula for the derivative is actually given in the formula book, but I want to talk about it because I think it's interesting to derive it and see where it's actually come from, and remind you like what it actually means. So essentially, we have some point x on a curve, and the curve is y is equal to f of x. Then this here is f of x. And what we say is I'm going to look at a point slightly further on, and it's going to be x plus h. H is going to be a small amount, but I can vary it. I can decide that. And then I'm going to find the gradient between these 2 points. So this here will be f of x plus h. And that means the gradient, which is delta y over delta x, is going to equal the difference in these values, so f of x plus h minus f of x, divided by the difference in these two, which is just h. But here's the key thing, and this is a fundamental idea in calculus, is that I can control where this goes. So I'm just going to move it closer and closer together until essentially they are the same points. They're not the same point, but I can let them be as close as I want. And that will mean that at that point, I will get the gradient of the curve. So basically, we get that dy by dx, then this is now an infinitesimal change in y divided by an infinitesimal change in x, is equal to the limit as h tends to 0. Okay, I'm just going to make it approach 0 without ever actually technically letting it equal 0. And this is what is given in the formula book. Okay, so now we've derived that, we can actually just use it. So it must be that f of x plus h is equal to 2x plus h squared, which is x plus h times x plus h minus 3. And I can expand that out. X squared plus 2hx plus h squared. Okay, and I'm going to expand this bit out as well. So therefore for us, sorry, this dy by dx didn't say this is the same as f dash x. It's just different notation. So f dash x is going to be the limit as h tends to 0 of this line here. And I've not left enough room. I'm going to have to move it along over here. So then I'm going to minus my f of x, which is this 2x squared minus 3. Now I need to put a bracket in here because I'm minusing the whole thing. Okay, I think that's a solid line to write down. Right, I'm going to move down here where there's a bit more space. So it's going to be 2x squared plus 4hx plus 2h squared minus 3 minus 2x squared plus 3. This is always the same sort of thing when you're differentiating from first principles. You always get these terms cancelling out. Oh, and that one and that one. And then you can either factorize the h from the top and then cancel out with the h, or just cancel them out like that. Because I'm adding, I can cancel it from this term, this term, and this term. If you factorized it, then it would be h 4x plus 2h over h, and then you would just cancel those two because I'm timesing. So the limit as h tends to 0 of 4x plus 2h, technically in a bracket now. And the key thing is that I can let h become as small as possible, so essentially I just get 4x as the answer. Okay, it's an interesting argument, and people took a long time to accept that you can essentially just let h equal 0 because it's the process of taking a limit. I'm not going to get into any more detail on limits here. It's just to the extent available, you can basically just get rid of the h. So that is my f dash x, and therefore f dash 2 is simply 4 times 2 is equal to 8. So I did all the hard work with x in, and this bit was actually very simple afterwards. Now, there is a second method, and I'm not going to do the whole thing again. I'm just going to tell you where we'd get to. So it would be actually right from the start to find that f of 2 is going to be it's going to be 2 times 2 squared minus 3. That's going to be 5. And then f of 2 plus h, because I'm trying to find f dash 2. So basically all these x's just get replaced by 2. And then that will equal, in fact, I would replace all of these by 2. That would be 4. That would be 4h. And, oh, I could simplify this, couldn't I, to 8. This is again going to be 5, actually. When I get rid of that and that to give me 5. So it'd be 5 plus 8h plus 2h squared. And then this would be 5, like I said before. And I'd be minusing 5, so they would just cancel. And this would be 8hx, but otherwise very, very similar. Here, like I've cancelled it out there, but this is now, sorry, not 8hx, sorry, just 8h, because x is 2. I hope this is making sense. So this is just 8h, and then I could, this is just 8, this is just 8, and then I would get 8 there. So I prefer doing it with x and then substituting in, because it's more useful to then apply to other things, and you're showing a more general case. So I don't actually personally think this is any easier. Maybe you prefer it a little bit because it's got numbers in, but I kind of feel like you can make more mistakes. So I would always practice it with x in. But that's just a brief explanation of what you would do if you wanted to go straight in and find f dash 2, not rather than working generally and then substituting x equals 2.